You're asking questions. Precisely. I have the real pleasure of introducing Jose Torero. Most of you have known, obviously, to everybody here. But I have to say that Jose is quite a brave man. He worked in the most hazardous work environment that you can possibly imagine. Hazard both physically and mentally. For several years, he had the office next to mine in the Department of Fire Protection Engineering. And I won't say that that's why he left the Department of Fire Protection Engineering, but other people have. So John Bryan, who was the chair, had carefully arranged the offices so that his office was at one end of a long line and mine was at the far other end. And poor Jose got sandwiched directly next to me and has suffered ever since. So with that, I guess, as an introduction, I guess we can start.
I have to say that's the best introduction that anybody has ever done of me, but anyway, I prepared this talk, and I think that what I was trying to do when I prepared it, and I hope I will achieve it towards the end, is bring everybody back to basics. I think that you've already probably noticed that there is some, I wouldn't say disagreement, but there is different concepts of really what makes or what doesn't make a good standard, and really what are the objectives of a standard. So I'm going to try to go back and try to redefine that concept and see if what comes after in the next presentations can benefit from that redefinition of what I believe makes a good standard. Now, obviously, this is not a generic definition that will apply to every possible standard. I think it's geared towards fire type of standards, but I'm going to use a simpler example to start with so that we get a little bit of a sense how in simpler problems we can define standards in a slightly better way. And once the problem starts getting complicated, then the definition of a proper standard or a proper assessment methodology becomes a lot more of a difficult issue, especially if we don't really understand clearly what is the physics behind the problem that we're trying to define. So basically the question is what makes a good standard? And I think that if I completely oversimplify the problem, and probably Vince will kill me for this, but basically I believe that a standard has to deliver the information it was designed for. So, we design a standard and we say, well, this is what we want the standard for, and to some extent it has to deliver that information for us. And clearly that doesn't mean much, because the question of what is the information, I think, is really the key question that needs to be asked. And for a complex problem like fire, it is very complicated to define what we want to get out of the standard. Now, there are certain common interpretations of that, and for example, one that is very commonly used is a relative assessment of performance. So we want to compare several materials, for example, and be able to say which one is better than another one. So we really don't care about the fundamental principles or the properties of the material or anything like that. We just simply want to be able to say, I believe this material is better than this other. Now, this definition is not full of problems. I mean, it does have a lot of problems. Now, another way to look at it is say we want to get out of the standard material properties, in the case, for example, of material flammability as an example, material properties that can be used for an absolute assessment of performance. In other words, I conduct a test or a standard, or I get some information out of the standard that then I can input, for example, into a model. And that model can use those variables to produce some sort of description or assessment of performance. So I can use it as a surrogate, something that I'm taking something out from to put into something else. And again, this is not a simple thing to do. I can actually even say that I can take, for example, material properties to be the input for fire models and be a little bit more specific. And I think we're doing this more and more, and I believe Jeff talked a little bit about fire models, and this is one of the real critical aspects about doing proper fire modeling, which is to be able to have the proper input variables that many times, for example, stem from the materials. So all these definitions can actually be used to define what really is the information that we want. But none of them really is a simple definition. They're all extremely complicated. Now, I'm going to give a simple example to just give you a sense how in other simple problems we can really address this in a fairly straightforward manner. So, for example, if I look into the area of energy conservation, and I'm talking about a house, and I want to be able to establish how good this house is in what concerns energy conservation. Then I'm talking about a very simple parameter, which in this particular case is heat losses. Okay? So I'm looking into heat losses coming out of the house, so I need to establish a mechanism by which I can quantify these heat losses, so that if I have different arrangements for the house, I can establish which arrangement produces less and which arrangement produces more heat losses, so that I can satisfy my requirements of energy conservation. So if I take that simple problem, and I ask myself the question of how do we assess performance, basically what I need to do, and the answer is pretty straightforward, is I need to be able to quantify the heat transfer. So if I'm going to model energy conservation, I have to be able to establish and quantify the heat transfer. I need to define the material properties that control the heat transfer. Once I have those material properties, I can introduce them into a heat transfer model, and that heat transfer model will actually tell me my heat losses that enables me to assess how capable I am of conserving energy. Okay? So if I look at this, I have to obviously simplify the problem because houses are extremely complicated. You know, they have complicated designs, they have angles, different materials, and a lot of things. But I can start looking one by one at all the components that actually are going to fit the house. So I start simplifying the problem by looking at the components, and for example, assuming that the transient period is negligible. So this is done very often when you have a system by which, for example, you're heating this place, and it is going to be a transient period, but then eventually the system is going to attain steady state. Okay? Once it attains steady state, it's going to spend most of its time at steady state, and then you can say, well, I can look into heat transfer in the steady state condition, and I can ignore the transient period. Now, I can look into the problem and say it's one-dimensional. So I'm already making simplification, and this is the process by which we standardize things. We start making simplifications. And we can say, well, walls have a narrow dimension, which is the thickness of the wall. So the heat transfer is in priority through that dimension. And then the other two dimensions are so large that heat transfer in this and in this dimension is negligible. So I can assess and quantify that and reduce my problem to a simple one-dimensional problem. So this is the problem. Here is your wall. Heat is going to flow only in this direction. Heat transfer in this and outside of the screen is negligible, so I have a one-dimensional problem that I'm assuming to be steady state. Okay? So then, basically, I have to solve Fourier's law, and it's just a simple differential equation with one single parameter, and that single parameter is the thermal conductivity. Okay? So the heat flux that is going to go through the heat transfer problem is basically the derivative with respect to the distance of x multiplied by one single material property, that is the thermal conductivity. So the energy equation that I need to solve is this one, and it's basically the steady state energy equation, where again the single parameter is x. The solution to this is a straight line. Okay? So this is basically what I need to do. Now, how do we make a standard out of this? So we need to find the value of k, because that is a single material parameter that will allow me to solve that equation and get the answer to my model. So basically we generate the ideal boundary conditions for this problem, and the ideal boundary conditions are a constant temperature at both ends. So I'm going to create, here is my sample, I'm going to fix the temperature here, fix the temperature there, wait until it reaches steady state when the answer is a straight line, and by doing that I can evaluate the value of k. Now, I have to solve the problem of the contact resistance, which is a little bit of a problem, because when you create these temperatures, something has to heat it up, and the contact between the two of them is not perfect. So there, the little problems of the standard start happening, because how is that contact resistance going to affect my ideal and perfect boundary conditions? Okay? So how do I do this? Here's my sample, and basically I have controlled heat sinks at both ends made of a material that is